So welcome. So we finished off our Kirchhoff's rules. And the reason, well, there's a couple of reasons why they want us to do Kirchhoff's rules, and one is because they use it almost immediately to do this next little bit. We've done capacitors before, but now we're going to do capacitors with a little bit of detail. So we need a Kirchhoff's rule for a capacitor. And so what we come up with, I'm sorry, I'm looking for my pen. What we come up with is we have a loop that, again, we invent. And we say if the loop exits the capacitor through the negative terminal, the potential difference across the capacitor is negative. So the loop, in this case, exits the voltage source via the positive terminal. So that would be a positive EMF. But that same loop is, because the negative is connected to the negative and the positive is connected to the positive, that same loop must be exiting the capacitor via the negative. So that is a negative potential difference. And when you add those together, negative cancels out positive, so it equals 0. That's what the loop rule says. So it makes sense. Okay. You can't really have a battery with a capacitor and analyze it as such. In steady state you can, but the process of charging involves current flowing down wires. And although we tend to think of wires as being resistorless, because it makes our math easier, there's always some resistance. So it's better for our analysis if we imagine a genuine resistor. And it's also, many circuits have a genuine resistor. So again, I'm using the international system, and that's a resistor. So we have a series combination of a capacitor and resistor, and we have an EMF, and we close this switch, and immediately the EMF is applied. So I can tell you, if this is 12 volts, that's 12 volts. This is 12 volts potential difference. That's 12 volts EMF. That's the way it works. But the interesting thing is that the 12 volts is not all applied across the capacitor or all applied across the resistor or 50-50. It depends. The equation that governs the capacitor is the capacitor equals the charge over the potential difference. So the potential difference is equal to the charge over the capacitance. So when you have no charge, you have no potential difference. The equation that governs the resistor is delta V equals IR. So when there's no current, there's no potential difference. So it's best to think of it in terms of the capacitor. Initially, let's plot this. Let's plot voltage across the capacitor. So initially, is there any charge on the capacitor? This is time. You close the switch, instantaneously is charge, excess charge, positive and negative. Is it there? No. So close the switch, no voltage. Is it easy to put charge on at the beginning? Yeah, it's kind of like like an empty parking lot. You can park anywhere you like. So yeah, my charge builds up quickly, so the voltage on my capacitor builds up quickly. So what I get in time is, whoa, I'm increasing my my charge, which means I'm increasing my voltage on my capacitor. But there comes a point when I'm saturated out. And so I would see the characteristic for my voltage across my capacitor looking like that. Yeah, I've got to do this. Let me ask you a question about the current flow. Initially, when there's a lot of charge flowing, is the current high or low? When there's a lot of charge flowing. Current's high. Oh. What happens as less and less charge can flow because the capacitors are more and more full? What happens to the current? Current gets low. So your current starts off high, but it falls off. That means if your current starts off high and falls off, your voltage starts off high and falls off. So when you close your switch, so this is my delta V resistor, and I'm going to do it in the same color, but this was my delta V capacitor. Can you see how they switch off? They both not switch off, they trade off. What do you think the product, not the product, the sum of those two always is? If I take the voltage drop across my capacitor and I add it to the voltage drop across my resistor, what do you think it always is? It's always going to be 12. It always adds up to the EMF. So in real terms, what happens is I start off and all the voltage drop is across my resistor and there's none across my capacitor because it's a high current and no charge on the capacitor. And then as time passes, eventually I have all the voltage drop across the capacitor because it's fully charged and no voltage drop across my resistor because there's no current flowing. So conceptually, I would like you to be able to tell me instantaneously, as soon as you close that switch, what's the voltage drop across the capacitor? And it's going to be 0 because there's no charge. As soon as you close that switch, what's the voltage drop across the resistor? 12 volts. Because all the current is flowing. And in a long time, what's the voltage drop across the capacitor? 0. Oh, I'm sorry. 12 volts because it's fully charged. And what's the voltage drop across the resistor? 0 because there's no current flowing. I'd like you to be able to conceptually give me those two ends. Yes?
You're saying 12.
Because I just...
In the resistor,
yeah.
In the resistor it's 12 and you shut it off because I guess the resistor's stopping it. Because you're turning it off, like stopping it.
No, it's because the capacitor's actually fully charged. There's nowhere to park another car. So the traffic stopped. It's actually all driven by the capacitor, actually. Mathematically, we can get that same understanding from using Kirchhoff's rules. EMF minus Q over C minus IR equals 0. Well, rearrange. E is equal to Q over C plus IR. That's like saying my EMF is equal to the voltage drop across my capacitor plus the voltage drop across my resistor. Okay, we just said that. When I'm at time t equals 0, my voltage drop across the capacitor equals 0, so all my EMF is across my resistor. At a long, long time, there's no current flowing, so there's no voltage drop across my resistor, so all my voltage drop is across the capacitor. In between, it's the sum of the two of them. Look at that. EMF minus Q over C minus IR. I is dQ by dt. We have an equation which has Q and dQ by dt. And what kind of equation is that? Isn't it differential? Differential equation?
Is that the E?
No, Q and dQ by dt.
Oh, I'm talking about the next one.
Okay? So, how do we solve differential equations? Well, we use differential equations, which is not part of this course. So, there's your answer. And I hate to do this. There's your answer. So, this is the form. It's the EMF times, what we said delta V Q over delta V equals C. So C times delta V equals Q. I'm not calling it delta V, I'm calling it EMF. That is my Q. So my Q is equal to my maximum Q modified by this exponential. The exponential is governed by this minus T over RC. When T is equal to RC, I have e to the minus 1. E to the minus 1 is what value? E to the minus 1, we go on my calculator, go blue, e to the x minus 1 equals 0.367. Oh yeah, I remember. That's my 37%. Yeah? For exponent. Oh, I see. At this time, I have 37% of my maximum value. Oh, I see. Okay. So this is discharging a capacitor, and I've fallen to 37% of my value at T is equal to RC. This RC I called my time constant. And it is literally the value of R times the value of C. It's really useful. If I have a 5 farad capacitor and a 10 ohm resistor, tau, which equals RC, equals 50 seconds. At time t equals 50 seconds, I have discharged to 37% of my maximum charge. If I'm more than 50 seconds, I've got in the 20s and the 10s left. Less than 50 seconds, I've got more. If I am charging, it's 1 minus what we just saw. Oh, 1 minus what we just saw. So my total Q, 1 minus e to the minus t over IC. Now my time constant is 1 minus 0.37, which is the 63% mark. In the time constant, I've charged up to 63% of my total charge. I want you to be able to tell me what's the voltage on the capacitor when you first close the switch. What's the voltage on the and the resistor when you first close the switch? I want you to be able to tell me what's the voltage on the capacitor after 20 minutes. I want you to tell me what the voltage on the on the resistor is after 20 minutes. I'd like you to be able to tell me the charges. What's the charge on the capacitor initially? What's the charge on the capacitor eventually? I'd like you to be able to tell me what the charge is in between using this equation. And if you think about it, if delta V, if Q over delta V equals C, then delta V equals Q over C. So you should be able to tell me what my delta V is in time. It's going to be E1 minus e to the minus t over RC. I've got a little alarm bell going off in my head, so let me just check this. Q over delta V equals C. Delta V equals... No, it's right. So learn these equations for charging and discharging, but be able to get your voltage by just dividing by Q. So know conceptually and be able to apply one or other of these equations. Okay? Any questions on that? Okay, let's end it.